So we're going to be looking at kind of an interesting and fun problem today regarding work and energy. We're mainly going to be actually focusing on work and forces, but it's important to note that work is simply the change in energy, but it is also equal to the force and the dot product between the distance it travels. So that means, work equals, again, so the force and the dot product of the distance is essentially the force times the distance it travels and the cosine angle between the two. So I want you to think about the concept of when we pull or push a block, we like to try to go parallel to the direction we're having it go. So if I'm going to pull a block, I want to pull it in the exact direction it's headed. And this has to do with the cosine angle. We essentially want that cosine angle to be 0 degrees because the cosine of 0 is 1, and this optimizes the amount of force applied on the block and lessens the work that we have to do. So our bodies actually intrinsically do this already when pushing or lifting or pulling objects. To mathematically illustrate the effect that angle has on the direction in which we apply a force to a block, we're going to go ahead, let's calculate how much work would be done on, let's say we have a 10 kilogram block. We want to pull it over a 12 meter distance. We're going to assume for the initial purpose that there's no friction, right? That doesn't actually exist, but in this hypothetical case, we're going to assume no friction between the block and the floor. And we're going to assume that we use a pull force, so we can like attach a light rope to that block, and we're going to pull it, and we're going to apply 50 newtons of force to that block. How much work would be done on the block if we're pulling directly parallel to the direction of motion, right? So that cosine angle is 0 degrees. We then just say, well, that's equivalent to the work is equal to the amount of force applied would be the 50 newtons, and we're going to multiply it to the distance, which is the 12 meters, and then the cosine angle between the two. We don't even have to calculate. Not cosine theta, cosine 0. So if I apply that force directly parallel, where the cosine of the angle between the applied force and the distance it's actually moving is 0, then I'm going to get a whole 600 Newton meter, which is the same unit as a joule of work. So this is also 600 joules of work. And this is going to be kind of our control. And we're going to change some variations to this problem and kind of look at what happens when we add friction, what happens if we change the angle on which we apply the force, and just minor details and how that affects the work and the force that we have to apply. And so what would happen if I decreased the angle at which I'm pulling the block? So my control was 0 degrees. It was directly parallel to the motion. But what would happen to the work if I decreased that angle by 30 degrees? Well, my work equation would then become the force times the distance, and then the cosine angle would become 30. And the force and the distance fully, when fully applied, is 600 joules, as we saw in the control. And we're going to take the cosine 30 degree of that, and we get something like 519 joules if we round. And then we'd find if we did the same thing again, so if we decrease it now into 60 degrees, we would get exactly 300 joules. And what do you think is going to happen if we decrease it to 90 degrees? So we go straight down to 90 degrees. We would actually get 0 joules. 0 amount of work is being done. And I want you to think about, what does that mean? Work is the change in energy. For all intents and purposes, there are the 3 kinds of energy we can discuss. We can talk about the change in potential energy, the change in kinetic energy, and the change in thermal energy. And for now, we're just really going to focus on the potential and the kinetic. The potential, well, the position of the block is not changing, and potential energy is all based on position of the block. The kinetic energy, well, the block is not moving, right? If I pull straight down, that block's just going to stay there on the floor. It's not going to go across the 12 meters. So it matters the direction in which we apply a force to an object determines the amount of work we have to do to get that object to move. For the rest of the examples of this problem, we are actually going to look at and keep the angle from the applied force in the direction of motion at 0 degrees. So the cosine is always going to be 0. We're going to have the maximum amount of effort put into our work on this block. we're going to look at, though, a few things. So if I have this example for the 10 kilogram block, I'm applying 50 newtons of force. It's going across 12 meters. I can actually use this. I can calculate the amount of time it's going to take to travel that distance. And I use that by using this kinematic equation right here. So I can set up my equation. My x final is equal to x initial plus v initial times t plus 1/2 a t squared. And by specifying, I can do two things for simplification. I can specify that it started at initial velocity of 0, so that makes that term go away. And then if I subtract the x initial term to the other side, I get x final minus x initial, which the final of anything minus the initial of anything is always the change in. So this then becomes change in my position, which is then equal to 1/2 the acceleration times time squared. And I can even go one step further in that simplification of that position. If I just say that my overall displacement is 12 meters, I can set my initial starting point to be 0. So I don't even care about where I started from, essentially, because I can set it at the origin. So I don't even have to write change in x. I can just write x, assuming that I know that that x is my 12 meters distance. So then I can say x is equal to 1/2 acceleration time squared, and then I just solve this equation for time. I'm going to multiply the 2 to the other side. I'm going to divide the acceleration, then I can square root the whole thing. What you'll end up getting is time is equal to the square root of 2x over a. And how can I put this in terms of my overall net force, right? Because I'm not given an acceleration, but I do know from Newton's most classic principle that force is equal to the mass times the acceleration. So I can set that expression up. Instead of using acceleration, I can use force. If I know that force is equal to ma, then I know that a is equal to the force over the mass. And all I do is I plug this expression in for a here, and what I end up getting is that the time is equal to the square root of 2x and the mass. That's not 2 times the mass, that's 2 the distance and the mass, over the net force. And the net force in this case, because I'm just considering the horizontal direction here, there's only one horizontal force, and it's the pull force that I'm applying to the rope. And if I calculate all of this, what I end up getting is I get the square root of 2. The distance traveled is 12 meters. The mass is 10 kilograms. To extend that there. And the force applied is 50 newtons. And so to set this up, a good practice that I like to do is I like to always check my units. So your units, if you set your equation up, should cancel properly. And what are we looking for? We're looking for time. So the only unit I want in the end better be just seconds. If I've set my equation up, it's going to end up that way. So what I'm going to do is I'm going to actually create 2 separate square roots here, one with just the numbers and the other with where the units are. So this is 2 times 12 times 10, and that's divided by 50. And I'm going to associate and attach to my units with it. The 2 has no unit, that's unitless. It was just part of the 1/2 right here. The 12 meters, so that's just a meter, a kilogram, is associated with the 10 kilograms. And the unit for Newton is kilogram meter per second squared. So that's a kilogram meter per second squared. And if you're unfamiliar with this algebra rule, if I have a denominator in a denominator, it becomes a numerator. So if I plug in all the numbers, what I end up with is 2.19. Associate my units here real quick. These meters cancel, these kilograms cancel. What I'm left with is, again, a denominator in a denominator becomes a numerator, a square root of a second squared, which ends up being a second. So it looks like we've set it all up, everything looks good. I have the unit that I want. And this is just a little trick into making sure you've set your final algebraic expression up properly. So we now know that if I apply a force directly parallel to the object of motion, assuming an environment where there is no friction, it's going to require 600 joules of work, and it's going to take 2.19 seconds to reach the end of the 12 meters. What if we were to add friction, and we said that that friction then required the time it took to travel the 12 meters to now be 5 seconds. What if we were able to use this difference to then calculate what is the frictional coefficient between the block and the floor if now we've added friction and now it takes 5 seconds, assuming we have changed no other variables? So the way we can calculate the frictional coefficient is actually, again, by using this same kinematic equation. And if you remember, our shortcut was to set it to equal x equals, we still have no initial velocity, so it's just equal to 1/2 at squared. If we remember that the net force is equal to the mass times the acceleration, and the net force is also equal to one other thing, right? It's equal to the sum of all of the forces. And so this is just capital sigma notation. It looks scary. All it means is I'm just adding all the forces together. So that is then also equal to essentially the applied force that I'm using, so the 50 newtons I'm applying to the block. We can use a subtract, let's just call that A for applied force. And forces are directional, so it's very important to understand their direction. So if I'm saying that A is in the positive direction, so that's going to the right, then the frictional force is going to counteract it, going to the left. This will be my frictional force. So I'm going to subtract from it my frictional force, and that's going to be my overall net force. And I can use this to essentially solve for my frictional coefficient. If I remember that my frictional coefficient function, my equation, is then, so the applied force minus the frictional coefficient equation is the frictional coefficient times the normal force. And what is the normal force of this block? Well, it's not floating off the ground, it's not dropping through the floor, so the normal force on the block is going to be equal in magnitude to the gravitational force. And the gravitational force on the block is just the mass times the acceleration due to gravity, because we're on Earth. And so I can set those directly equal to each other, so then I have the applied force is then subtracted from it, the frictional coefficient, the mass, and the gravity, instead of saying the normal force. And all of this, again, is equal to the mass times the acceleration. So then if I put it all together, I get that the mass times the acceleration is equal to the applied force, which is just that 50 newtons. Remember, we haven't changed anything except for we added friction, and we knew it took 5 seconds. So we subtract from that, then the frictional coefficient, the mass, times the gravity. If I solve this equation for A, I'm going to divide the mass through each term. A is equal to the applied force over the mass minus the frictional coefficient times the gravity, because the masses cancel in that second term. And I can plug this in here to my equation up here. So my position is equal to 1/2, instead of saying acceleration, I'm going to say applied force over mass minus the frictional coefficient times gravity times time squared. And what am I solving for? I'm solving for the frictional coefficient. So at this point, it's just algebra. I'm going to move the 1/2 and the time squared to the other side. I get 2x over time squared. That's equal to the applied force over the mass minus the frictional coefficient times gravity. I'm going to subtract everything from the other side. I'm going to do this in 2 steps, but I get the frictional coefficient times gravity is then equivalent to the applied force over the mass minus 2 times x over time squared, and then I just divide the gravity through each term. So I get then the frictional coefficient is equal to the applied force times over the mass times gravity, and I'm going to subtract from that 2x over gravity times squared. And that's my final formula for finding the frictional coefficient. And for this
Specific problem, frictional coefficients have no units. So when I check out my units and I do that trick like we did before with the time, my unit, my last number, all my units should cancel. What I get should be unitless. All right, so what I have is I have my applied force. That is a 50 newtons over my mass, which is 10 kilograms times 9.8 meters per second squared. And if you're asking yourself why is the 9.8 not negative, it is because I've already taken direction into account by subtracting the applied force from the frictional force. So if you already take that into account, you don't need to add that additional negative sign. What you just need to ask yourself is, what does that negative mean? That negative denotes a direction. That's all that negative means. And if you've already taken into account all the directions, you don't need to apply it twice. So then I'm going to subtract from that 2 times my distance, which is 12 meters, over the 9.8 meters per second squared, times that time squared, which I said in this case, it took 5 seconds. I want to find the frictional coefficient if it takes 5 seconds applying the same force. So this is now 5 seconds squared. What I'm going to do again is I'm going to set all my numbers up first, and then I'm going to set all my units up so we can see how the units should cancel. Again, I should get something that is unitless. So the frictional coefficient mu should be equal to 50 over 10 times 9.8, and I'm going to subtract from that 2 times 12 over 9.8 times 5 squared. And again, my units, so my associated units are going to be Newton, which is, if we remember, a meter per second squared, right? So that's second squared. The kilogram from my mass down here on the bottom, and then I have a meter per second squared again, and remember, a denominator in a denominator becomes a numerator, so that becomes second squared, which it looks like everything cancels. This cancels, the meters cancel, and the seconds cancel. I end up with something unitless. Perfect. The second one should also cancel. It's important. We can't add or subtract things together that are of the same unit. So then what I get is a meter on top. I have a meter, again, seconds, second squared is in a denominator and a denominator, so it's in the numerator, second squared, and then this seconds is also being squared, so second squared. I end up with a unitless number, and the actual value of which, when I plug into my calculator, becomes 0.41, which is then again the frictional coefficient for this specific object, which is actually in a standard range for that you would see of something like carpet. Now that we know the frictional coefficient, let's calculate the new work that's acting on the block. We have that the work is equal to the force times the distance and the cosine angle between the two. We're taking it still to be cosine of 0, so it's a 1, so it's just work is equal to the force times the distance. And this is the net force. So if I have a frictional coefficient on the block, then my net force is no longer just the 50 newtons. My net force is now what we saw as previous, the applied force minus my frictional force, which we found was the mu mg, and that is all going to be multiplied by the distance now. And I can figure out my new calculated work. I have all my terms here. What I find out is that I have 50 newtons minus my unitless frictional coefficient 0.41 times the mass of 10 kilograms times, I'm running out of room here, let's move this over, times the gravitational pull, 9.8 meters per second squared, and all of this now is going to be multiplied by the distance, so the 12 meters. So again, I'm going to set up just my numbers and then just my units. The units should all cancel. 50 minus 0.41, 10, 9.8, and all of that being multiplied by 12. And my associated units with it, instead of saying newtons, I'm going to say kilogram meter per second squared. I'm going to be subtracting from it. I have kilogram meter per second squared, and that's perfect. And then I'm multiplying it by a meter. So if I then plug this in, and I plug it into my calculator, what I end up with is 117.8, and this ends up being the unit is kilogram meter per second squared times a meter. And if we remember, kilogram meter per second squared, that is a Newton. So this is the same as a Newton times a meter, and a Newton times a meter is also the same unit of a joule. And we want our work is energy, we want it to be in joules. So it's 117.8 joules. Now you might be saying to yourself, well, it's 117.8 joules. That's a lot less work than 600 joules. Why is the work less if I've added friction? And what you want you to think of, you yourself haven't actually worked less. Your applied work on the block is still 600 joules, because that is the amount of force and effort you're putting on the block. The block's overall net work is 117.8 joules. What does this translate to in terms we can understand? The block's going to move a lot slower. Where is the rest of that work going? Friction. Friction is taking that work, it is turning it into thermal energy. It's turning it into heat. If you rub your hands together really fast, friction takes that energy and it converts it into heat. And the difference between that, how much work is friction taking? Well, it's directly proportional. So 600 joules minus the 117.8 joules, and we see that friction is taking 482 roughly, if we round, 65 joules of energy. That's how much energy it's taking, and this is again with some rough rounding. But what we're able to see there is that the energy didn't just disappear, it went somewhere. It went into heat. Now, if I were to say I want to take this work energy problem, I want to then take this same block, I want to increase the force I apply on the block so that it then crosses this carpety surface area, or this frictional surface area, with, in the same amount of time as before, right? The 2.19 seconds. I want it to then cover that same distance in the same time. How much more work would I need to apply to the block? Well, you'd need to apply the same amount that friction is taking out. The additional work you would need to apply to the system is 482 joules. You need to put that much more effort into pulling the block over the same amount of time and same amount of distance. And this is actually why we use things like weights, why you can add things like friction, why runners train, they can train into headwinds, like running straight into wind is harder than running with the wind. Is for this very reason, it applies and requires more work for the system.